Okay, well, let's look at y derivative. I noticed that my cute little picture down here is kind of slow. I scratched my nose, half an hour ago or so, and it's just now showing it. But uh, let's take a look at just something really simple. Here's a pretty simple question. So I made this graph. Uh, y equal x squared, f of x equal x squared. And I thought, well, I don't want to put it right here at the origin, and so I moved it 2 to the right and up 1, and decided to go with this graph, this g of x here. So it's parabola, but it's just been moved over. And now suppose that this was some sort of cost curve. I'm in business or something like that, and I I've made a mathematical model, and I believe somehow my cost is going to kind of follow this function. Maybe these ones, twos are actually hundreds or thousands or millions of items or something like that, and if I start producing more, maybe I already own a great big building or something like that, and as I produce more, it doesn't really cost very much for me to keep producing more, and so sort of that average cost, maybe this is the average cost per item or something, and that average cost just keeps going down. But maybe once I hit this many, 200 or 2,000 or 2 million or something, I have to start doing things like adding a little space somewhere, renting a little space, and renting more and more space and so forth to make more, and so that average cost starts going up maybe, and so I'd really like to produce this many, but again, this may be in a model and part of something bigger, and not so easy to just draw like this, because it may involve more variables and so forth. And so what we want to look at is sort of why derivatives. This chapter 2 is about derivatives. Why derivatives? Why do I care? And you can look up lots of things about instantaneous rate of change and all that. But again, why do I care? Why not just get an estimate or something like that? Well, it really comes down to the usefulness of that number, and if we can calculate it just fine, then maybe it comes in real handy. And so, for instance, we take a curve like this. Now, what I did was I called this m of x, and I have this thing called g prime of x. Well, that's this thing we're going to study, the derivative. And m, I'm calling the slope. I'm not going to, well, I can show that. It's sort of uninteresting at this point, but it happens to be a straight line. But what I'm interested in doing is at every given point C along the x-axis here, now I'm only going from 1 to 3, I'm going to make this straight line, and notice that straight line, it's the point slope form. X equals C is a point, and then g of C. So I have a point on this curve. I can see that from the C, g of C right here. And then the slope is this thing up here, evaluated at C. Okay, we don't know what that is yet. It's this thing called a derivative, but what's nifty is if I look at that line, it hits here on the curve, g of c. I knew that should happen because that's c and that g of c for my point slope part. That's the point part. And then what's interesting is if I use this slope, no matter where I move that point C, it turns out that slope gives me this nice effect of giving me the general trend at that point. Okay, it tells me, right, I know things are increasing here, things are going up, but this line is kind of showing me if I use this straight line, then right at that point, this might be a really good straight line to use. Okay, so that's what this particular straight line is showing me if I make it this way. And why might this be a good straight line to use? Well, notice what happens as I let's see, what I'm trying to do is I guess when you zoom in far enough it kind of loses that dot, but so this is at 2.54, so I'm right here. But notice what happens is as I zoom in really close, I can't really see the difference between these two lines, right? Here I can see a little bit of green there, not so much in other places. If I make sure I stay centered on the 2.54 where C is, I just don't see but one line, right? And if I make that disappear, there's the green line, put it back, the black line's on top. And so if I was going to use a straight line right in this vicinity, I guess I would use this straight line. This would be a nice one. And so now I'm going to zoom back out. And you see when we're zoomed out, well, no, that straight line looks nothing like the function itself. But it does in really small areas. Okay, so as I look at this line, it gives me a good idea of sort of, at least in a very, very small area right here, kind of what's going on, right? It gives me the point, C, G of C, right? And it tells me quite well what that rate of change is approximately in there. And okay, so that's very nice, and that's a good thing. We'll look more and more at that. But for now, though, let's just kind of look at the line on the whole and say, well, remember, I wanted to know this point here, this bottom point. Well, notice what happens to that black line when I'm right at that point. Well, if I can get right at 2, I'll make it a 2. Right? That line becomes horizontal. Well, certainly it seems like it should, because here I was going down. I was going down until I got to 2, and then I was going back up after 2, and that's what made this the lowest point, right? I was coming down to it and then going up to it, going up from it. If that didn't happen, it wouldn't be the lowest point. And so with that, as I zoom in, of course, what's it going to look like? Well, because I had to flatten out, in order to go from decreasing here to increasing, I had to flatten out at that spot. And that's what that black line is showing us is, oh, yeah, okay. That black line saying, yeah, I had to flatten that out. Well, so if I know, so if I could tell you for all these different black lines, which we call the tangent line, for all these different black lines, if I could tell you exactly which one had a slope of 0, then I could tell you exactly what that point is, right? Because if I know which line has a slope of 0, I would know then what C and G of C were to make that line. Okay, in particular, I would know very easily what y equals G of C, because if that's 0, the other disappears. It's a constant. But I would also know the C because, well, if I could tell you when this m of C, that derivative, when that is 0, if I can tell you that, then I can tell you at what value of C to look at for the minimum. Now, that's only a possibility, because if I turn this thing over and made it a maximum, I would have a very similar picture, but it narrows things down, right? I know the minimum's not there. I know the minimum's not up here. I know the minimum's not there, right? It has to be at this spot where my line has a slope of 0. So I want to look for where that thing's 0. Now, if I turn this back on, it actually becomes a bit more interesting, because this is my function. So for each x, I am computing, what that derivative should be. And notice right there, at 2, it's 0. And of course, 2 is where that minimum occurs here. And so by knowing where this function, m of x, is equal to 0, I can tell you something about this function and where it reaches, say, a minimum or possibly a maximum, something like that. That's a big deal. I don't know if you think it's such a big deal, but I think that's a really big deal, because now all of a sudden I have a way to find that minimum that I didn't have before. Okay, so if I can actually tell you what this thing is. Now why? Well, because what I want to do is, and I probably get an error from doing this, but what I want to do is look for where that m of, well, I'll write it as the g prime of x equals 0. Oh, and it was very happy. Notice if I turn off some of these other things, what it did. I don't think Desmos will always do this, but here it said, oh, it's at 2. That's awesome. Okay, so I could solve that equation. So Desmos, it doesn't always solve equations. Now, I think the reason it solved this equation is, for instance, if I said 2x plus 3 equals 0, it solves that equation, right? And x, well, make it a minus 3, so we'll get a positive 1.5. So it solves that equation. However, I think if I simply go to x squared, ooh, it solved that equation as well. I'm surprised, but that's great. So it solved that one. Well, let's try to get something a little, let's take it up to a cube. Does it still solve it? It solves that one. What if I add in x squared plus 3? Now, oh wow, okay, this is exciting. So this is moving a little away from what we were talking about, but we're trying to set something equal to 0, and this darn thing came up with an answer. That is very exciting. Desmos didn't used to be able to do that. See what happens if I give it something like sine of x. Wow! Okay, people, this is exciting. We'll probably be able to use this. But at any rate, so it solved this, and we got x equals 2 as an answer. And again, if we put this back in there, right, that is right where that minimum occurs, and all we had to do was solve this little equation, which in general, equations aren't real bad to solve with technology. Some are pretty nasty, but technology does a pretty good job. And heck, I've just learned that Desmos, it has upped its capability in solving equations, so that's really nice. And so we'll try to use that at times. But here, so see, I just ask it, solve this equation. It tells me at 2, and so now I know the minimum occurs at 2, and I can tell you what that minimum is. It's 1. So there you go. Now facetiously I can say, oh, I guess we don't even really have to do much in chapter 2. But yes, we do. We again, as we've seen with technology, you can't just trust that the technology will do it. As I said, this feature here, the fact that it did that, that is a very new feature, probably within the last year and a half. So that's quite exciting. And given I just realized it's doing this, I don't know how good it is. It might be very good, but then again, it might not be. I don't know. We'll have to see. But there we go. I started with this function. If I can tell you where that instantaneous or rate of change, or what we call the derivative, if I can tell you where that's 0, I can tell you good candidate places for minimums on curves or maximums on curves. And as I mentioned to begin with, we want to model things with mathematics, and so, like I say, this could be the average cost curve for a business, and we would like to know where that reaches a minimum, because sure, wouldn't I like to produce where the average cost of production is the smallest? Yeah, I think I would. So we want to be able to solve problems like that. So that is one reason why we want to know more about this thing called a derivative, or the instantaneous rate of change. Okay. So exciting.